So good morning. Thank you for coming. As Abby mentioned, we're going to talk today now about the Space Weather Technology Research and Education Center and its initiatives in space weather here at CU. We are, as Abby mentioned, a grand challenge center that was formed about a year ago. This was a Chancellor's initiative to bring space weather into a focus at CU. CU's been involved in space weather a long time. Boulder is sort of the epicenter, if you will, of space weather and space physics in the nation. We have the NOAA Space Weather Prediction Center here at Boulder. We have the High Altitude Observatory, the National Solar Observatory, CU, of course, Southwest Research Institute, lots of different groups around Boulder and at CU doing space weather. This is CU's attempt to really provide a focal point for people like you from the external community who want to engage in space weather related topics at CU. So we put in a proposal, like I said, about a year ago, myself, Jeff Thayer, in the aerospace department, and Dan Berger, we're sort of co-leading this effort. Dan is, of course, the director of LASP. And we've collected a lot of collaborators here at CU in the meantime in this last year. And we're developing more and more external partnerships as we go along and looking forward to even more. So coming to an Aerospace Ventures Day, I always like to start with what is space weather, because it's a little strange to talk about weather all of a sudden when you've been talking about robotics and mechanical engineering, electrical engineering, computer science. Space weather is really the interaction of the Earth with the sun. And this is a movie of the sun taken in ultraviolet light in September of 2017, showing one of the largest eruptions on the sun in the last 20 years. And as you can see from this little blue dot, maybe you can see that or not, I don't know, but that's about the size of the Earth in relation to this solar eruption. So what you're looking at is a 10 million to 30 million degree plasma eruption off the sun going into interplanetary space. That's called a coronal mass ejection in the lingo of the field. And when those coronal mass ejections happen to come towards the Earth, as this one did not, because you're looking at the sun and it went off to the side, so this one missed us. But had it hit us, this would have created a lot of trouble here on Earth in terms of technological operations, particularly for space-based systems. So we always like to show this kind of a slide where we see up at the top here the sun, and here's a coronal mass ejection coming off. What happens when these things come towards Earth is the first thing that arrives are the photons coming at the speed of light, and those consist of a lot of X-rays. And a lot of the X-ray radiation coming off of that flare and coronal mass ejection ionizes the atmosphere excessively, and all of a sudden the ionosphere is no longer a good radio reflector. Radio communications drop out, over the horizon radar drops out, all sorts of havoc is wreaked upon communications technologies at that point. GPS becomes flaky because the ionosphere is heated and turbulent. That's the immediate effect. Once this big cloud of plasma arrives, sort of 15 to 45 hours later, depending on its speed, it also does all sorts of things. It pushes radiation ahead of it. That radiation, in terms of protons and electrons, starts interacting with satellites. You can get solar cell degradation. You can get upsets of computers. It loads up the Van Allen radiation belts, so anything orbiting in the Van Allen radiation belts, which is everything, is now all of a sudden exposed to a lot more radiation than it was previously. And satellite systems become unstable in some cases, or even fail in large events. Going further down into the atmosphere, some of this radiation can even penetrate into the atmosphere and stratosphere, particularly in the polar regions where it's sort of funneled down by the magnetic field. And if you have a polar airline flight going over the pole at that time, those passengers and crew are going to be subjected to higher levels of radiation than normal. And in fact, during a large event, airlines are now rerouting around the poles for this very reason. And then it goes all the way down to the ground. These giant magnetic interruptions, if you will, of the magnetic field of the Earth and the ionosphere create electrical currents, which drive giant currents in the ground as well. And so you get induced geoelectric field and currents, which can actually interact with the power grid and destabilize it in the worst case. In 1989, 2003, there were blackouts due to solar eruptions, destabilizing power grids in Canada and Sweden. So that's kind of an overview of what we call space weather. And as you can see, it's sort of a huge amount of physics that you have to know in order to understand and predict these effects on the Earth. You have to go all the way from being able to understand and predict a solar magnetic eruption, as we call it, which causes these flares and coronal mass ejections, all the way down to solid Earth geophysics, understanding how currents are transmitted into the ground.
I'm just reminding you of that.
Ah, thank you.
Thank you.
I'll stand here, maybe that's a little better. And so it really is a sun to mud physics problem, as we call it. Now, as a problem statement, this is just a summary of what we sort of say space weather is. The environmental conditions in near Earth space, driven by interactions of the Earth's magnetic field and atmosphere with the sun's radiation, magnetic field, and plasma outputs. Turns out the Earth's atmosphere also interacts with the near-Earth space by gravity waves and other things caused by thunderstorms. So you actually get space weather coming from below and above. It's a very complex nonlinear problem in linkages in that sense. But the basic problem statement behind space weather and why CU chose to focus on this and why the nation actually chose to focus on this a few years ago with executive committees and now some bills going through Congress is that we're sort of 50 years behind terrestrial weather forecasting in our ability to know when these things are going to erupt from the sun, what they're going to do when they get here, and there's various reasons behind that. Number one, as I mentioned, it's a huge range of physics to understand and predict. So it's not just, like terrestrial weather, you have this little sort of 60-kilometer shell that you can, work with, and it's a chaotic system where you can put in initial conditions and you can figure it out pretty good 5 days out. This is a driven system all the way from the sun down to the ground. So it's a much more difficult physics problem. One of the bigger issues here is the lack of observations, though. The number of satellites out there, the number of instruments used that are actually operational, meaning they're 24/7 and can be relied upon for predictions, can be counted on one hand. So you'll see these NASA slides where they show this huge fleet of spacecraft out there exploring the sun and space, and they say, we're researching space weather like never before. Only 2 of those spacecraft can be used for forecasting because they're constantly operational. The others are all science satellites that occasionally drop down data and take 6 or 8 weeks for scientists to plow through the data. That's not a forecasting system. So another thing here is that there's getting the big picture of all these data together is really difficult. And so you'll hear later about some efforts we're putting into something called a data portal, which collects all these disparate data sets together so scientists and forecasters can understand these events a little better. Tom Baltzer from LASP will talk about that in a bit. There's also a lack of full system coupled models. If you can imagine, you need models that go all the way from the sun down to the ground, and they need to be coupled together so that they can feed the forecasters the information. And so this is really an area where Tim Fuller-Rowell at Ceres and others at SWPSI are working to couple atmospheric models into space models, and Tim will talk a little bit about that in a bit. And finally, there's really a lack of research to operations feedback mechanisms. In other words, the operators in the forecast office say, well, we have this problem, we really need this sort of solution. That doesn't often get to the researchers very efficiently. So that's one of the key areas that the CU Center hopes to focus on, is that linkage between operations and research. And one of the things that you'll hear about here is that satellite operators need to know when the atmosphere is swelling and shrinking due to space weather. And right now they don't really have a good way of doing that. They have empirical models that don't really work when there's a storm. So we really need to get better with predicting satellite drag and helping operators do that. And you'll hear from Eric Sutton this morning about some work we're doing, and Vishal Ray as well, to understand what a satellite is doing, especially in low Earth orbit as it plows through this changing atmosphere due to space weather. So again, one of the bottom lines here is there's really no dedicated academic centers of excellence in space weather until the Chancellor chose to put one here at CU. So we are the Space Weather Technology Research and Education Center, and we've sort of organized ourselves into 3 large enterprises here. One is the research enterprise. As I mentioned, we're working on a full physics satellite drag model to replace the empirical, very approximate models that are currently used by the Air Force and others to track satellites. Again, Eric Sutton will talk more about that. We also are developing a space weather deep learning laboratory in which we'd like to use very sophisticated convolutional neural network techniques for video. You have to have time series video fed into neural networks to understand things like solar eruptions. One of the biggest holes we have right now in space weather is there is absolutely no way to predict a solar magnetic eruption, the source of the major space weather. We can sort of see it happen, and then we can predict when it's going to hit the Earth. We'd like to actually predict when it's going to happen. Right now, that's at the level of earthquakes. We sort of watch it happen and say, gee, it would have been nice to predict that. I think we have possibly the data to do that in terms of the real-time solar dynamics observatory data, the movie that I showed at the beginning, constantly looking at the full sun. But that's, as you can tell, that's a time series problem where you have to feed video, essentially, images of a time series into a predictive system. So I think deep learning could show some promise there. We've got a nascent effort there to develop some of that technology. Then we have what we call the Missions, Applications, and Data Technology Enterprise. This is looking at better ways of observing space weather, better ways of getting the data together. As I mentioned, Tom Balter is going to talk a little bit about our data portal effort here. And then finally, getting these NASA missions out there, which like to tell people that they're doing space weather, getting their data into the forecasting office quicker, so that instead of 6 weeks, it can take 6 hours or even 2 hours or maybe even real time eventually, to help the forecasters understand what's going on. If not for forecasting, for nowcasting, which is just as important as forecasting in some sense. If you're sitting in the middle of a big hurricane, you'd like to know what's going on and when it's going to be over. You know, maybe you missed the forecast, but now that it's here, what's happening? So there's a lot of NASA data out there that's really good for that, but it doesn't get to the forecast office because there's no linkage there. We hope to be that linkage in the future. And then finally, we have the education enterprise. Being in a university, of course, one of our mandates is to educate the next generation workforce. And understanding what space weather is, how to forecast it, and why it's important is a big part of Trek's mission. And so we're developing a space weather graduate certificate. We're also intimately involved in the Boulder Space Weather Summer Schools. There's 2 here, one by the NSF called the Boulder Space Weather Summer School, descriptively enough. And there's another one called Heliophysics Summer School by NASA. That's also run here in the summer. That's a little bit more of a graduate level summer school. This is more undergraduate and possibly professionals. We get some forecasters coming through this one as well. So we're helping develop material for that. And then finally, we have plans. We have not started this, but we have plans to do a professional master's degree, something like an online degree for professionals who would like to learn more about space weather, get a certificate, a master's that says, yeah, I really understand what this is about, and can go back to their industry groups and what have you to further develop new ideas. And so that's about it. I think what I'll do now is turn over to, I believe Eric is next up on satellite drag. Thank you.